All right, so last time I was doing one example on ruled surfaces. I got stuck somewhere. I figured it out, what was wrong, and I changed my notes. So you may just find it, on the web page, the corrected notes. I will not do it here again. And my notes does it in the general case. Okay, so the general case of this, so this is a hyperboloid of one sheet. So something like this, okay. And it tells you what the rulings are. Okay, so if you have any questions about it, you may just ask me later. Okay, so today we will start new section 4.3, differentiable functions. Functions and tangent vectors. Okay. We start with the lemma. Now let alpha be a differentiable curve, differentiable curve. In a surface M. So that its image lies in the image XD of a surface patch of a single surface patch. Then there exist differentiable functions. There exist unique differentiable functions. A1 and A2 on I, so that alpha t is given by x of A1t, A2t for all t. So what does this tells us is the following. Suppose this is our surface and we have some interval and a curve alpha, so that the image of this curve lies inside the image of a single surface patch, let's say x of d. And what is d? D is a region in R2, and this is a surface patch. Okay. What this lemma tells us is the following. You can make this diagram commutative. So you can find a function. Suppose the image of this curve alpha is this, okay? Image of alpha. This lemma tells us that you can find two functions, a1 and a2. So this is just, okay, let's say t. So I have a function here. So this is a1t, a2t, and the image of alpha is just the image of this composition. So alpha t is just x of a1 to a2t. Okay, a1 to a2t is, let's say, this point. This is t, and this is alpha t. Okay. Of course, this is not a surprise because this is a homeomorphism. Therefore, x has an inverse, so I can just go backwards, and first I come with alpha, and then I go with x. Then I will obtain this a1, a2. But the statement is that these are differentiable functions. Okay, we know that x is a homeomorphism, but it's not a diffeomorphism. Well, it can't be a diffeomorphism. Okay, well, to the surface, it can be a diffeomorphism, but not to R3. Okay, let's talk about the proof. Let's see how it goes. As I said, consider the differentiable function. X inverse composition alpha. So I go first with alpha, and then by X inverse, right? So I first go with alpha, and then via X inverse, I land in D. Okay. D is the region in R2, therefore it has two coordinate functions where this composition is just A1T, A2T for some functions. AI from I into R. Okay, so of course from this, just composing both sides with X, right? Taking X to this side, we see that hence alpha T is just X of A1T, A2T for all T. So the only thing we need to show that these two functions are differentiable, and they are also unique. Okay. Okay, let's see. Uniqueness comes from okay. Okay. Well, I am not sure actually why x is differentiable. For uniqueness, it's easy. If let's say alpha t is equal to x of, let's say, b1t, b2t for some other functions, then of course we have what? We have x of a1t, a2t is equal to x of b1t, b2t for all t. But then since x is an inverse, apply x inverse to both sides to get what? A1t, A2t equals B1t, B2t for all t. And this finishes the uniqueness part. To see that A1 and A2 are differentiable, okay. What can we do for that? Surface patch'imizin şey olduğunu biliyoruz. Differentiable bir fonksiyon. Görüntüsüne de homeomorfizm. Ama tanımında x inverse'ün differentiable olması diye bir şey yok. Gerçi şey bir dakika, orada bir gariplik var ama x regular tabii. Regular olduğu için de bir dakika, ne yapabiliriz? Notları onlarla ilgili hiçbir şey yazmamışım da ona kafam takıldı. Bir saniye. Şuna bir bakayım. Okay. Yani aslında şöyle bir şey yapabiliriz de. for differentiability, okay, let me change the board. We may proceed as follows. Okay, so okay, now I have this map from D into R3, okay, and what we know is that differential of this, so X star from the tangent space to XD to R3 is injective. At all points. Okay, so here is D, and here is its image, let's say in R3. And the differential map is injective, okay? At any point, the tangent map is injective to XP. Okay. Okay, we may extend this X to a function in R3. How? Consider the function big X from D cross R into R3 as follows. So if I have, let's say, T here, T demeyeyim de buna başka bir şey söyleyeyim. Okay. S diyeyim. I send it to the following point. So this is X of P plus S times gradient of X, okay, at P. So what you do, I have the gradient vector here, gradient vector, and I add a third direction here, third direction, and as I move, you know, in this direction, I will just add this guy to that point. So I will move from this surface. So something like this. Okay. No, in the gradient direction. So when S is 0, I am here. When S is positive, I will just move in this direction. So I will come to a point like this. X of P times S times the gradient vector. Now, if you compute the differential of this, at the point P comma S, what you get, well, X of P has 3 coordinates, x1, x2, x3, right? And then you have what? Derivatives of this. So del x1, del bunlara UV mi demiştik? UV demiştik değil mi? UV del x1 del U And then I have, of course, a third component here. This component, okay, with respect to P, no, with respect to U, so, okay, S times derivative of this gadget with respect to bir dakika, bu gradient dediğimiz şey nedir? X1'in yok, gradient vektörü olmaz o ya. Değil mi? Şey kastetmiştim ben. Gradient değil de. Şu olabilir. Tangent vektörlerin çarpımı. Şuradaki normal vektörü alayım. NP olsun bu. NP NP'nin U'ya göre türevi. NP dediğim şey şu. NP şuradaki tangent vektörlerin x sub U ile x sub V'nin cross product'ı. Tamam. Sonra V'ye göre türev alacağım. Evet. Del x bir dakika. Burada komponentların türevini alacağım, değil mi? Del x1 yok. İlk komponenti bunun nedir? Şöyle yazayım. Bir saniye. Bunun komponentleri nedir? X1 P and then S times bu N'nin ilk komponenti. Evet. Şöyle yazmakta fayda var. Burada XP plus S times NP. So this is X1P, X2P, X3P plus S times N1P, N2P, N3P. P dediğim şey artık tabii ki şu. UVS. Okay. Now when you take derivatives of this, X star. So I take the first component and take derivatives with respect to U, V, and S. Derivative of the first component is just x1 plus s times x1 plus s times n n1 uv. Here this is x1 uv and then değil mi? Şunu da şöyle daha açık yazayım. So x1 uv plus s times n1 uv. This is the first component. X2 uv plus s times n2 uv, comma, the third component, x3 uv plus s times n3 uv. This normal vector is a function of u and v only. The third variable s only comes up, here, s. Okay. So when you take the derivatives of these functions with respect to u and v and s, so derivatives of this with respect to u, v, and s will be what? So it will be just del x1 del u plus s times del n1 del u. So this is the derivative with respect to u. Derivative with respect to v, and then derivative with respect to s. So uv. Okay. And then del x2 del u v del u s times del n2 del u x2 times del x2 del x v s times del n2 del v, and here I have n2 uv, and then x3 uv s and 3 del x3 del v plus s times del n3 del v and n3 uv. Now I will compute this at the point, so x star uv, and then I take 0 here. So when I take 0 for s, these terms will disappear because I have the s component here. So the first row is just the first tangent vector, basically. Del x3 del u, and then when you plug 0 for s, you get del x1 del v, del x2 del v, del x3 del v, and here I have n1 uv, so n1, n2, n3. Now what is the determinant of this gadget? So at the point uv 0, okay, this is just the vector x, derivative of x with respect to u. Second column is derivative of x with respect to v, and the third column is the normal vector to the surface. Normal vector to the surface. But what is the normal vector? This is just xu cross xp. And when you take the determinant of this, what is the determinant of this? So x star uv0. Determinant is the following. You take cross product of any two vectors and take dot product with the third one. Cross product of these two, and then the dot product with the third one. Well, it is the same thing. So what is this? This is just x sub u cross x sub v norm squared, but our surface is regular, meaning that this is never 0. This is a positive number, so this is positive since x is regular. What I am trying to do is the following. I have a surface patch defined on this piece of surface, and it goes into R3, right? This is our x. What I do, I define a thicker function. So defined on D cross R, okay? I just thicken the domain by R. So it is defined on the space, 3 space, UV and S, okay? UV and S, so that the restriction of this to UV plane is still little x, but it is more than that. Okay, note that. Okay, let me change the board. Note that x is a function defined on the tree space, right? It is defined on R. This is a subset in R2. So R2 cross R, which is R3 into R3. So let's say this. And derivative at UV0 is an isomorphism for all UV in D. Therefore, by the inverse function theorem, X has an inverse because the derivative map is never zero. Okay, hence X has a local inverse. From some subset U into let's say V. U is an open set. U in R3 is open, containing the point P, and V is an open set. No, this is containing the point X of P, little x of P. This is an open set containing P in D cross R. Okay. Maybe I should write P comma 0 for the S coordinate. These are open sets, and this is the inverse of big X. Moreover, big X restricted to the plane S equals 0 is just little x. Okay, so this UV0 is little x UV. Okay, it's by the definition of X, right? When if S is 0, you just have only X of P. Okay. Well, now what we know is then is the following. Hence, by the inverse function theorem, this big X is differentiable. So that is big X tersi de differentiable. Çünkü yani big X zaten differentiable da inverse function theorem diyor ki tersi de differentiable. So that buradan ne söyleyebiliriz? O zaman küçük x ne olacak? Küçük x şimdi şöyle diyeyim. X of UVS neydi? X of UV plus S times normal vector, right? Normal vector. Therefore, if I put big X in here, I will get this, and this is just UVS. No. And if you let S is 0, so let S equals 0, I get UV 0, which is just X inverse X of UV plus 0. So I get this. This means, you know, this was already a homeomorphism. So this guy had an inverse, and that inverse has to be X inverse. So that little X inverse is just the restriction of a differentiable function on R3 to the surface M. So I have a differentiable function from R3, an open set in R3, I should say, and this goes into D cross R, which is V, D cross R, and my little x inverse is just the restriction of this to the surface M, right? M is a subset of this U, okay? Therefore, this little x is also differentiable. Hence, x inverse is differentiable. What I mean by that, it is the restriction of a differentiable function to R3. Therefore, the coordinate functions of this are differentiable because they are the coordinate functions of this differentiable function. So when we come back to okay, what was okay? So here x1 neredeydi o? A1 and A2. Ha şurada. A1 and A2 X inverse'de alfanın kompozisyonu. Alfa differentiable zaten. X inverse'de differentiable. Dolayısıyla da kompozisyon differentiable. Onu da şöyle yazayım şimdi. Okay, let me change the board. Okay, now finally, since A1t, A2t is just X inverse composition alpha t, and X inverse, little X inverse is just this function restriction to M is differentiable. So are A1t and A2t. Okay. So this finishes the proof of the lemma, I guess. Somehow in my notes, I just, skipped that part. Okay. So this finishes the proof. Okay. Of course, we can make use of this fact we just proved for, for other purposes also, not just for the proof of this lemma. So what we have proved is that if you have a surface patch, the inverse of the surface patch is the restriction of a differentiable function from R3 into R3. Okay. Okay. Here is another result. If x and y are overlapping surface patches, in M, then there exists unique differentiable functions u bar and v bar such that one surface patch can be written in terms of the other surface patch. For all uv in the domain of x inverse y. So what is this? This is my surface, let's say, and I have two surface patches with overlapping images. Suppose this is x of d1, this is y of d2. So this is x and this is y. Okay. So what does this tells us? That if you have any point, let's say the coordinates are u and v, and this common region, let's say, is this region, this one, and it corresponds to this one. Okay. So okay. What does this tells us is the following. If you choose any point here, let's say uv, so it is this point yuv. Of course, it comes from a point here, right? It comes from a point here. what is that point? That point is just, there are some functions u of uv and v of uv. So here is the function u bar v bar, taking the point uv to this point, u bar uv, v bar uv, and x of this is equal to this gadget. So x of this point is equal to y uv. But you know, this is basically the same actually problem we had in the proof of lemma. By definition, u bar v bar will be just what? I'll just take x here, x inverse y, and uniqueness will be as before. And for differentiability, when you put x bar here, you know, you have to say that this is a differentiable function. But we know that since this is a surface patch, x inverse is the restriction of a differentiable function to the surface. Therefore, this function is differentiable. Y is differentiable. Therefore, the composition is differentiable. So u bar v bar is a differential, are components of a differentiable function. So the same proof basically works. So let me just write down the proof. As in the proof of previous lemma, we may assume that, right, we proved this, we may assume that x inverse is differentiable. It is the restriction of a differentiable function to the surface. Hence, the composition, hence the functions u bar v bar, u bar uv, v bar uv, defined by u bar uv, v bar uv. So I define these as follows: x inverse of y of uv are differentiable. And clearly, you know, this u bar v bar satisfies this equation, right? They satisfy this equation because you just take this x inverse to the side. And uniqueness can be seen easily also. So this finishes the proof. Okay. You know why this is important. This shows us that, you know, actually any surface patch is basically reparameterization of another surface patch, right? X is a surface patch, Y is another surface patch. Wherever they intersect, one of them is actually a reparameterization of the other one, right? X is just what? It is this parameterization, right? X is just reparameterization of Y actually, right? Instead of putting, you know, some, well, let's say AB here, you write u bar of uv and v bar of uv, where u and v are the variables of the parameterization y. Okay. Yeah, sure. Why is that? Because, you know, intersection is just the restriction of x to an open set, right? For this to be a surface patch, you need what? You need x has to be 1-to-1. It has to be a homeomorphism onto its image, but it was already a homeomorphism on this bigger set. So when you restrict it to a smaller set, it is still a homeomorphism. And the derivative of x has to be 1-to-1. Well, that's a pointwise condition, right? Derivative of x is pointwise on the whole set. Therefore, it is 1-to-1 on at all points on this smaller set. Okay, restriction of a surface patch to a smaller one is always a surface patch. But the nice thing about this theorem is that basically all surface patches are the same. Okay, just a variable change, a reparameterization of the surface patch gives you other surface patches, right? You may change this x. You may put any surface patch here, but you see that that is just y, okay? Changing this x will change these parameters. Okay, let's have a break. After the break, I'll continue.